So today we are talking about geometric means. We're going to continue to add a tool to our toolbox today for the right triangles. Yesterday we talked about the Pythagorean theorem, okay, when to use the Pythagorean theorem. It's a right triangle, and you know two sides, you're looking for the third side. Okay, so that's when you use the Pythagorean theorem. Now, before I tell you how to use geometric means, I want to tell you what a geometric mean is. A geometric mean comes from a geometric sequence. Okay, and a geometric sequence is when each consecutive number is found by multiplying the previous number by a given factor. So what's happening here in this pattern? What's happening in this pattern? You're multiplying everything by 3, right? Okay? And so that's a geometric sequence. Okay? Now, within a geometric sequence, you have geometric means. The number that comes between two others in a geometric sequence is called a geometric mean. Now, that's a different mean than what we're used to. Okay? And to find it, what you can do is you can set up a proportion with the numbers on either side and find out what that geometric mean is. Okay? And so, like, this acts as my A and this acts as my B in the proportion below. And so I could say that 5, this is my x, 5 is to x as x is to 45. So 5 is to x as x is to 45. Okay? The geometric mean shows up twice in the proportion, and it's always diagonal with each other. So you cross multiply, and you get 225 equals x squared, and you take the square root of both sides, and x is 15, which is what we found it to be, right? What it was in our geometric sequence. So, if I just say find the geometric mean between these two numbers, okay, what would I do here between 4 and 9? 4 is to x as x is to 9. And so we cross multiply, and we get 36 equals x squared. You take the square root from both sides, and you get x is 6. All right, on this one you do the same thing. 6 is to x as x is to 15. When you cross multiply, you get 90 equals x squared. You take the square root of both sides, and how do you break 90 down?
3.
3, no, 3's on a perfect square.
Oh.
9 and 10, and so you end up with 3 radical 10 for x. Okay, so I'll tell you how this all applies to the triangle in just a second. But I need to tell you something else first. The scenario which we're working with today is you've got a big right triangle, okay, triangle XYZ, and you have the altitude drawn from the right angle of the right triangle. YW is drawn from the right angle of the right triangle. So when that happens, you create 3 similar triangles. You have the big triangle, which is triangle XYZ, and it is similar to the medium-sized one, which would be XWY, which is similar to the smaller one, which would be YWZ. Okay? So when you have that right triangle and you drop that altitude from the right angle, you create 3 similar triangles. And what do we know about similar triangles? The corresponding angles are congruent and the sides are proportional. Okay? So you can set proportions up to find the missing pieces. Okay, so let's write a similarity statement identifying the 3 similar right triangles in the figure. Now all I've done is basically flip this over. Okay, I'm going to just identify those so I can keep them straight. If I looked at the big picture, I would have triangle ABC. And it's similar to, how would you label the medium-sized one? Not ABD, it would have to be ADB. And the reason is because the B is the right angle in the big triangle, so your D is the right angle in the medium-sized one, okay? And they both share A. Okay, what about the small one? What would it be? BDC, okay? BDC, because the C has to match up with the C in the big one, right? So it's got to come last, and then my right angle is at D. D kind of tags along. All right, so when you have the big right triangle with the altitude drawn, you get 3 similar triangles, and those corresponding sides are proportional. Now, you can set up proportions, and that's what we're going to do. You can set up proportions according to that. I find it kind of hard to see. I almost, just in my mind, I have to redraw the triangle. So there's an alternative way to do it, and that is by using geometric means. And it's a little tricky at first, but once you get the hang of it, it's not that hard. It's just one of those things you kind of got to work through. And so within your triangle, within your big right triangle with the altitude drawn, you have two different geometric means. Actually, you have three, but two different types. Your altitude is a geometric mean. Okay? This altitude, when you draw it, it breaks the hypotenuse into two parts. And when you draw it, it breaks it into two parts. This is a geometric mean between both of those parts. So A is a geometric mean between H1 and H2. So I can set up a proportion. H1 is to A as A is to H2. Remember, the altitude is a geometric mean. It shows up twice. Okay, it's diagonal with each other. It is the geometric mean between the both parts of the hypotenuse that it breaks into. So let's give these some values. Let's say that I want to find my altitude, and let's say that this is 6 and this is 2. How can I set my proportion up?
6 over x, Trevor.
6 over x as x is to 2. Now he said, does it matter because you do 2 is to x is x is to 6? No, that's fine. Just that the geometric means have to be opposite, diagonal with each other, okay? So we cross multiply and we get 12 equals x squared. And then we take the square root, and 12 breaks into the square root of 4 times the square root of 3, which is 2 radical 3. Okay, so that's one geometric mean. Okay, we have another one, or another type, and it is our leg. And both legs work, okay? But the leg is the geometric mean between both parts of the between the part of the hypotenuse that's adjacent to it and the whole thing. Now remember, big picture, you have a big right triangle with the altitude drawn. The altitude breaks the hypotenuse into two parts. But this time, the leg is the geometric mean between the closest part of the hypotenuse and the whole hypotenuse. Okay? Both of those pieces touch that leg, okay, at the end point. So it's the closest part of the hypotenuse and the entire hypotenuse. So my L1 is the geometric mean between H1 and C. The other leg is also a geometric mean. And it's the geometric mean between its closest part and the entire hypotenuse. Okay? So it's a geometric mean between the closest part and the hypotenuse also. So L2 is a geometric mean between H2 and C. So let's work a problem. Let me put some numbers in here. Let's say that we want to find the leg, and let's say that H2 is 4 and H1 is 6. Okay? Now, remember, the leg is the geometric mean between what two things? H2 and the whole hypotenuse, right? And what's the length of the whole hypotenuse? 10, right? So what's my proportion going to look like? Remember, the geometric mean shows up twice, but it's diagonal with each other. 10 is to x as x is to 4. So it's the geometric mean between this part and that part. Okay? So 10 is to x as x is to 4. Or you could do 4 is to x as x is to 10. We cross multiply, we get 40 equals x squared. Take the square root of both sides. How are we going to break 40 down? Okay, 4 and 10. And so So x is 2 radical 10. All right. So let's do a couple of more. Because like I said, this takes a little bit of practice. Okay, so we look at this next problem. Now, don't forget what we learned yesterday. Because yesterday we learned that if you had a right triangle, okay, and you know 2 sides of it, you can find the third side by using the Pythagorean theorem. So we can apply that today also, okay? But first of all, look at the big picture. It's a big right triangle. We have an altitude that's drawn from the right angle of the right triangle. So I want to find x first. Let's find x first. What do I know about x? It's an altitude, which means it breaks the hypotenuse into 2 parts. And what do we learn about the altitude? It's the geometric mean between the 2 parts of the hypotenuse, which in this case are 20 and 5, right? Okay, so what would my proportion look like? 5 is to x as x is to 20. So that altitude breaks the hypotenuse into 2 parts, and it's a geometric mean between both of those. So I end up with 100 equals x squared. We take the square root of both sides, and so what's x going to be? 10. Okay, so we found this right here to be 10. Now, we want to go and find y. Now, y can be found in 2 different ways. What would you like to do? Pythagorean theorem? Okay, so he or she, I want to say that. He's wanting to do the Pythagorean theorem, okay, because we have a right triangle here, and I know the 2 legs. So what would that look like? I couldn't hear who said that, sorry. 5 squared plus 10 squared equals y squared. So I have 25 plus 100 equals y squared. So I have 125 equals y squared. I'm going to take the square root of both sides. What am I going to break 125 into?
45.
25 and 5, right? And so that ends up being 5 radical 5. But I didn't use geometric means to set that up. Yes, what would that look like? We won't work it out, but what would that look like? 5 is to y as y is to 10, no. Because it's between the geometric mean between the closest part and the whole thing, which is 25. So it would have looked like this. 5 is to y as y is to 25. Okay? You could have done it like that. Let's do the other one as geometric means, the Pythagorean theorem. How would we find z using geometric means?
Z is to 10.
No.
20 is to Z.
20 is to z
Z is to 25.
as z is to 25. Good. Because this is the geometric mean between the closest part of the hypotenuse and the whole thing. Okay? So it's 20 is to z as z is to 25. So we cross multiply and we get 500 equals z squared. We take the square root of both sides, and how are we going to break 500 down? 100 times 5, right? Okay, and so the square root of 100 is 10. So z is 10 radical 5. All right, let's do another one. We look at the big picture. We have a big right triangle, right? We have an altitude drawn from the right angle of the right triangle. What do we know about that altitude? Okay, it's the geometric mean between both parts of the hypotenuse, right? Okay. All right, so somebody on this side of the room, tell me how I'm going to set my proportion up. Eric.
X is to 8.
No, we're doing Z. We're finding Z.
Okay. Z is to 25. Is 8 is to Z.
Okay. I'm gonna do 8. You're right. 8 is to Z as Z is to 25. That's fine. He said Z is to 8 as 25 is to Z, and you can do that too. Either way, it's the same thing. Okay. All right. So cross multiply here, and we end up with 200 equals z squared. Okay, so remember this z breaks the hypotenuse into two parts and is the geometric mean between both parts. So we take the square root, and how are we going to break 200 down, Kaylin? Okay, so the square root of 100 times the square root of 2, and we end up with 10 radical 2. Okay, so this is 10 radical 2. All right. So now we need to find either x or y. What do we want to find next? X. What are we going to do? You want to do the Pythagorean theorem? Okay. So we're going to do the Pythagorean theorem. Okay. And so how would I set that up? 8 squared plus 10 radical 2 squared equals x squared. Okay? So we get 64 plus, what is 10 radical 2 squared? Okay, 10 squared is 100, radical 2 squared is 2, 100 times 2 is 200. Okay, so we end up with 264 equals x squared. Take the square root of both sides. And what goes into 64? 8? I don't think 8 does. 264 divided by 8. Doesn't. Well, 8 does, but 8's not a perfect square. 4 and 66. Okay? So 4 goes into it. And so we end up with 2 radical 66. We wouldn't want to do 8, right? I mean, we could if you were going to do a tree. If you want to do a tree, go ahead and do the 8. But
That's 64.
but 64 won't work either.
I know, but you said 64 instead of 260.
Oh, maybe I just rambled it together. I meant 264. You should have known that's what I did, right? Yes? It ended in a 64, and 4 does go into that, so that should, because that's the divisibility rule for 4, right? If you look at the last two digits, and 4 will divide into the last two digits, it goes into the whole number, and 4 is a perfect square, right? Okay. How about y? Let's do geometric means this time. How are we going to find y using geometric means? 25 over y as y is to 33. Because the whole thing is 33. Okay, so we cross multiply, and 25 times 33 is 800 something. 825. And we take the square root. But really, we got to go back and break it apart. What's it going to break into? 25 and 33, right? 25s are a perfect square. Okay? So this breaks into the square root of 25 times the square root of 33. And it ends up being 5 radical 33. Okay. Last one. This one's kind of neat. Okay, so again, we've got big picture. We've got a right triangle with the altitude drawn. Okay, what should we find first? You want to find z first? Okay, how? Is it a triple?
Yes.
It is a triple, isn't it? Okay, and so this is what? 3 times 3, 4 times 3, so this is going to be 5 times 3. So my z is 20. No, 15. I'm getting ahead of myself. My z is 15, sorry. Okay, so what should I find next?
X.
X? Okay, how am I going to find x?
That's 12 over x and x
Okay, the 12 is the geometric mean between 9 and x. So could we set up a proportion? Yes. What would that look like? No.
x over 12.
9 is to 12 as 12 as to x. We knew the geometric mean this time, so it's not our unknown, but it still has to show up twice, okay? So we cross multiply, and we get 9x equals 144. Divide both sides by 9, and we get 16. Now, since this triangle was a triple of the family 3, 4, 5, and all these triangles are similar, what should be true about them? They're going to be all triples, aren't they? Okay? of 3, 4, 5. So what are they multiplying through this time with? 4. 3 times 4, 4 times 4, 5 times 4, and so my y is 20. Okay, so 2 geometric means. One is the altitude, and what's the geometric mean between? What's the altitude, the geometric mean between? The two parts of the hypotenuse, right? The leg is the geometric mean. The leg is the geometric mean between what? The closest part and the entire hypotenuse, right? You gotta add the parts together, okay? All right. Your assignment is on page 541.